In Lesson 13, we're going to be working with square roots. Now we're taking a bit of a break from solving quadratic equations, and I'm just going to introduce square roots and some of the things we'll be doing with square roots. Then Steve is going to return to quadratic equations and talk about using square roots to solve a particular type of quadratic equation. And finally, Candace will end this lesson with some applications. So I'm going to start by talking about finding square roots, simplifying square roots, and I'm going to end by talking about rationalizing the denominator. So let's start with finding square roots. So what's the square root of 36? Well, verbally, the square root of 36 is the non-negative number that squares to 36. In symbols, we write it like this. The square root of 36 is 6. Since 6 squared equals 36. Now we know that the square of negative 6 also equals 36. But when we're talking about square roots, we're just interested in the non-negative number that squares to 36. Some lingo here. This thing that looks like a check mark, we call that the radical sign. The expression under the radical sign, in this case 36, is called the radicand. But 9 times out of 10, I call it the expression under the radical sign. Now sometimes we say radical 36 instead of the square root of 36, or sometimes we just say for short root 36. So this is just some of the lingo you'll hear when we're talking about square roots. Now why are we talking about square roots? Well, we're solving quadratic equations. Suppose we're asked to solve x squared equals 36. Not a lot of work is involved. We know what the solutions are. The solutions are 6 and negative 6. Both those numbers square to 36. Where do square roots come in? Well, 6 is the square root of 36. The second solution will be the opposite of the square root of 36. So we'll see some square roots as we're solving a particular type of quadratic equation. So here's the formal definition. The square root of a equals b if b squared equals a and b is greater than or equal to 0. By definition, the square root of a is non-negative. That's why we have this condition on our definition. Also, when we square a square root, we get the radicand back. We get the number or expression under the radical. This is what it means to be a square root. So b, this number b, is called the principal square root of a. So when we said the square root of 36 equals 6, this is the principal square root, even though when we square negative 6, we also got positive 36. An expression such as the square root of 48 is called a radical expression. We could have a number under the radical sign or even an algebraic expression under the radical sign. Again, here's our radical sign. The expression under the radical sign is called the radicand. If a is a perfect square, then the square root of a is rational. And if a is not a perfect square, then the square root of a is irrational. And we'll see lots of examples of this in the lesson. So let's evaluate the square root of 169. To do this problem, I need to ask myself, what non-negative number do I square to get 169? Well, since I know a lot of my perfect squares, I know that 13 squared equals 169. So the square root of 169 is 13. So as you're working through the problems that go with this lesson, it really helps to know some perfect squares. How about the opposite of the square root of 2 times 50? Now back when we talked about the order of operations, we mentioned that the radical sign is a grouping symbol. Here's where we're going to start using that. So the opposite of the square root of 2 times 50, doing the multiplication under the radical sign first, this is the opposite of the square root of 100. So now, what non-negative number do I square to get 100? Well, that would be 10. So this simplifies into the opposite of 10. Whew, big expression under the radical. Let's simplify that first because the radical is a grouping symbol. So I have the square root of 10 squared minus 4 times 5 times 5. Well, order of operations. I'm going to evaluate that power and perform the multiplication. 4 times 5 is 20. 20 times 5 is 100. Under the radical, I just have 0. And what non-negative number can I square to get 0? Well, that would be 0. The square root of 0 is 0. The square root of 1/9. Now this is a little bit trickier because I'm thinking about fraction arithmetic. What number can I square to get 1/9? Well, remember when we multiply fractions, we multiply the numerators and we multiply the denominators. So I'm thinking my numerators both have to be 1, and 3 times 3 is 9. So 1/3 squared is 1/9. Going backwards, the square root of 1/9 is 1/3. Here I have that symbol plus or minus. This means I'm looking at two numbers, either plus the square root of 36 over 121 or the opposite of that. And as we start solving quadratic equations using square roots, we'll see this symbol quite a bit. So when I simplify this, I'm really doing two problems at once. And now I have to think, what two fractions, or what fraction, do I multiply by itself to get 36 over 121? Well, the fraction has to be the same. 36 is a perfect square. 6 times 6 is 36. And 11 times 11 is 121. So 6/11ths squared is 36 over 121. Working backwards, this will simplify into either plus or minus 6/11ths. How about the square root of negative 144? Well, let's think about it. We know that 12 squared is 144. We know that the square of negative 12 is 144. Both of those numbers give us positive 144, not negative 144. The only other type of number I can square besides a positive number or a negative number is 0, and 0 squared is always going to be 0. So I cannot square a positive number and get a negative result. I cannot square a negative number and get a negative result. And I can't square 0 and get a negative result. In fact, there's no real number that will allow me to do this. So what I would write here is the square root of negative 144 is not a real number. Now, the reason why I can write this conclusion is I know that there are some numbers which are not real that can be squared to give me a negative number. You'll see those in your next algebra class. The square root of a negative number is not a real number. How about the square root of 7? Now, 7 is not a perfect square. I can't think of any natural number that I can square to get 7. But I do know some things about the square root of 7. For example, I know that 7 is between 4 and 9. Both 4 and 9 are perfect squares. So this means that the square root of 7, which I'm interested in, is between the square root of 4 and the square root of 9. So I know that whatever the square root of 7 is, it has to be between 2 and 3. Now at this point, I could pull out a calculator to get a decimal approximation for the square root of 7. So on my calculator, if I take 7 and find its square root, I do indeed get a decimal approximation between 2 and 3. I get 2.6458. So the square root of 7 is approximately equal to 2.6458. Now my calculator was just showing 5 digits. If your calculator is showing 12 digits, you need to remember that that's still an approximation. The square root of 7 is an irrational number, and it cannot be represented by either a terminating decimal or a repeating decimal. Now what I'm going to do here is kind of show you that this is an approximation. What I'm going to do is I'm going to calculate the square of my decimal approximation. I'm going to take 2.6458 and I'm going to square it. And notice that I don't get exactly 7. That's an indication that the number I've written on my paper is just an estimate. The calculator gives approximate values for irrational numbers. How about the square root of 28? 28 again is not a perfect square, but 28 lives between two perfect squares. It's bigger than 25 and it's less than 36. So what does that tell me about the square root of 28? Well, the square root of 28 is going to be bigger than the square root of 25 and less than the square root of 36. So the square root of 28 is going to be between 5 and 6. I know that much about it. Let me get a decimal approximation using my calculator. So entering 28 and taking the square root, I get approximately 5.2915. Now notice this number is a little bit closer to 5 than 6, and that's because 28 is closer to 25 than it is to 36. Now one of the things about 28 is 28 has a perfect square factor. This is 4. 28 is 4 times 7. And we're going to use this to simplify the square root of 28 some. So this is my next topic, simplifying square roots. And to do this, I'm going to use what we call the product rule for square roots. If a and b are non-negative real numbers, then the square root of the product of a and b is equal to the product of the square root of a and the square root of b. We can also go the other way. If we have the product of the square root of a and the square root of b, we can rewrite that as the square root of the product. Let me show you how we can use this to simplify the square root of 28. We just observed that 28 has a perfect square factor of 4. So I can write 28 as 4 times 7 and put that expression under the radical sign. Now I'm going to use the product property of square roots and write this as the square root of 4 times the square root of 7. Well, since the square root of 4 is a perfect square, that's just 2. So I can simplify the square root of 28 as 2 times the square root of 7. Now let me show you something. What I'm going to do is I'm going to square 2 times the square root of 7. Now when I do this, I should get 28. This is what it means to be the square root of 28. So distributing that exponent, 2 squared times the square root of 7 squared, 2 squared is 4, and the square of the square root of 7 is just 7. So I'm just confirming that I have a good simplification here. So now let's simplify the square root of 80. So I'm going to do the same trick. I'm going to pull out a perfect square factor of 80. Well, 4 divides into 80 evenly. So I can rewrite the expression under the radical as 4 times 20. So this is the square root of 4 times the square root of 20. Well, the square root of 4 is just 2. But now when I look at this, I notice that 20 also has a perfect square factor of 4. So it looks like I can go a little bit further. I can write the square root of 20 as the square root of 4 times 5. So this is 2 times the square root of 4 times the square root of 5. Square root of 4 is 2 again. 2 times the square root of 5. Whew. Lots of steps to get a simplification of 4 times the square root of 5. Now, nothing wrong with those 1, 2, 3, 4, 5, 6, 7 steps I took to simplify this, but at the beginning, I might have noticed that 80 also has a perfect square factor of 16. And if I made that observation, it would have taken a fewer steps. The important thing is just to simplify until you no longer have any perfect square factors under the radical. Let's do this again. So now I have radical 3/4. Does 3/4 have a perfect square factor? Well, it does, 1/4. In fact, 1/4 is 1/2 squared. So I'm going to write the expression under the radical as 3 times 1/4. This is radical 3 times the square root of 1/4. From our observation, the square root of 1/4 is just 1/2. So this is radical 3 over 2. Now there's another way to do this problem. We also have a quotient rule for square roots, which says that if a and b are non-negative real numbers and b is not equal to 0, then the square root of a quotient is the quotient of the square root. We can also go the other way. If we have a quotient of square roots, we can write that as the square root of the quotient. Let's see how we can use that to simplify the square root of 3/4. So the square root of a quotient is equal to the quotient of the square roots. And in the denominator, I have a perfect square under the radical. So I can write this as the square root of 3 over 2. A couple of steps fewer than the other way of doing it. Both ways get me to the same simplification. Now let's simplify the square root of 9/5. Using the quotient rule for square roots, this is equivalent to the square root of 9 over the square root of 5. The square root of 9 is 3. So I've simplified my expression. The last thing I'm going to talk about is rationalizing the denominator. We just simplified the square root of 9/5, and we ended up with 3 over the square root of 5. This particular expression has an irrational denominator. 5 is an irrational number. The radicand's not a perfect square. And in some situations, it's not helpful to have an irrational denominator. So even though there's really nothing wrong with this, sometimes the results in our algebra book are written with rational denominators rather than irrational denominators. So when we're asked to rationalize the denominator, we want to end up with a rational denominator instead of an irrational denominator. And when you're working problems, you'll probably want to do this so that you can check your answer with somebody else who might be rationalizing their denominators. So what we're going to do is we're going to multiply the given expression by some form of 1 in order to obtain a rational denominator. Let me show you how we're going to do that. We have 3 over the square root of 5. Now all I can do is multiply this by 1, but what form of 1? Well, if I multiply the square root of 5 by the square root of 5, that is the square root of 5 squared, which is, by definition, 5. But if I multiply the denominator by the square root of 5, I have to multiply the numerator by the square root of 5 as well. Here is my form of 1. In the denominator, we have the nice rational number 5, and in the numerator, we have 3 times the square root of 5. So now we have a new algebraic, or new expression, equivalent to our original expression, but now there's a rational denominator. Now we haven't gotten rid of the irrationality. We still have an irrational factor in the numerator. This number is still irrational, but we have a rational number in the denominator. The reason for putting a rational number in the denominator is historical. Before people could get decimal approximations quickly using a calculator, the computation they did by hand was a lot easier if they had a rational number in the denominator. But even though we all use calculators for working with irrational numbers now, this is just carried over historically, and you'll still see it in most of your algebra books. So let's work a few examples of rationalizing the denominator. 35 over root 7. I want to multiply this by an appropriate form of 1. I want to get rid of that square root of 7 in the denominator. The only way I can do that is by multiplying it by another factor of square root of 7. But I also have to multiply the numerator by the square root of 7. So I have 35 square root of 7 over 7. Now I can simplify this a little bit more because I notice that 35 factors into 7 times 5. And I can pull out that 7 over 7, and I'm left with 5 square root of 7 over 1. 7 over 7 is 1, and this simplifies into 5 square root of 7. Now in this particular example, you can see that what I ended up with is a little bit simpler than what I started with because I no longer have a fraction. So in some situations, rationalizing the denominator can actually help simplify things so that further work with this number is a bit easier. So I'm going to work this next example in two ways. I'm going to start by just working like I did in the previous example. I'm going to take 1 over the square root of 18, and I'm going to multiply it by the appropriate form of 1 to get rid of that irrational number in the denominator. I'm going to multiply this by the square root of 18 over the square root of 18. So now I have the square root of 18 in the numerator and just 18 in the denominator. Now, I want to simplify this. 18 has a perfect square factor of 9. So I'm going to rewrite the numerator as the square root of 9 times the square root of 2. 9 times 2 is 18. I'm using the product rule for square roots. The square root of 9 is 3. And I have a factor of 3 in both the numerator and the denominator. 3 goes into 18 6 times, so I end up with a square root of 2 over 6. Let me do this problem another way. Now when I do this, I'm going to start by simplifying the radical expression in the denominator first before I rationalize the denominator. So the denominator is equivalent to the square root of 9 times the square root of 2. We saw that in the previous way we did this. So I have 1 over 3 times the square root of 2. Now, the only radical factor in the denominator is root 2. So I'm going to multiply this expression by the square root of 2 over the square root of 2. So now I have the square root of 2 in the numerator, and in the denominator I have 2 factors of the square root of 2. Well, 2 factors of the square root of 2 is just 2. So I end up with the square root of 2 over 6. That's precisely what I got doing it the other way. I ended up with a rational denominator, and the one radical I have in my final simplification has no perfect square factors under the radical. Another example, I'm going to work this 2 ways again. So I have the square root of 6 over the square root of 99. The first way that I'm going to work this is I'm going to simplify both radicals first and then rationalize the denominator. So square root of 6, there's not much I can do with that. 99 does have a perfect square factor, 9. So I'm going to rewrite the denominator as the square root of 9 times the square root of 11. 9 times 11 is 99. So now I have radical 6 over 3 times radical 11. Radical 11 is my only irrational factor in the denominator. So I'm going to multiply both the numerator and the denominator by the square root of 11. So in the numerator, I have the square root of 6 times the square root of 11, and in the denominator, I have 3 times 2 factors of the square root of 11. In the numerator, radical 6 times radical 11 is the same thing as radical 66. That's the product rule of square roots again. And in the denominator, I have 3 times 11, so I end up with radical 66 over 33. Now at this point, I'm done. I cannot do anything with that 33 and 66, even though I see that 33 divides into 66 evenly. I'm just going to leave it like this. I'll say a little bit more about that when I do this the second way. Now, how else could I do this? Well, the square root of 6 over the square root of 99, I could start by using the quotient rule of square roots. This is the square root of 6 over 99. Now I have a fraction under the radical, and I can simplify that fraction under the radical first. Well, that fraction reduces. Both of the numerator and denominator have a factor of 3. This reduces to 2 over 33. Now, breaking this up again, this is root 2 over root 33. Rationalizing the denominator, I can do that by multiplying both the numerator and the denominator by the square root of 33. I did that because root 33 times root 33 is 33. And using the product rule for square roots in the numerator, the square root of 2 times the square root of 33 is the square root of 66. Going back to what I had in the previous way, I got the same thing. The square root of 25 over 28. I want to rationalize the denominator, but I'm going to start by writing this as the square root of 25 over the square root of 28. Square root of 25 is 5. The square root of 28 I can simplify. This is the square root of 4 times the square root of 7. So I have 5 over 2 times the square root of 7. Now I'm ready to rationalize the denominator. I'm going to multiply my expression by square root of 7 over the square root of 7. In the numerator, I have 5 times the square root of 7, and in the denominator, I have 2 times 7, which is 14. Now in this one, I'm going to confirm this result on the calculator. I'm just going to show that our original expression and our final simplification give us the same, we get the same value on our calculator. So the first thing I'm going to do is take the square root of 25 over 28. 25 divided by 28. Let's take the square root of that. That's 0.94491. Now let's evaluate this expression. 5 times the square root of 7, and then divide that by 14, and that's the same number we got from our original expression. One last example. The opposite of the square root of 1/75. Now this one's a little bit easier than some of the ones we were just doing, but I put it here for a reason. Using the quotient rule, this is the opposite of the square root of 1 over the square root of 75. And as students are working with square roots, they sometimes forget the easy ones. The square root of 1 is just 1. So when I'm working with this expression, I'm just going to worry about the square root of 75 in the denominator. And I'm going to simplify before rationalizing. So 75 has a perfect square factor of 25. 75 is 25 times 3, so I can rewrite the denominator as radical 25 times radical 3. So this is minus 1 over 5 times the square root of 3. To rationalize the denominator, I need to take care of that factor of the square root of 3 in the denominator. I'm going to do that by multiplying both the numerator and the denominator by radical 3. And I end up with minus radical 3 in the numerator, and in the denominator I have 5 times 3. So these two expressions look quite different. Which one is simpler? Well, that's kind of a judgment call. I think what we started with looks a little bit simpler, but at least here we have a rational denominator. So now I'm going to turn this over to Steve, who's going to solve some quadratic equations using square roots.